Hi there and welcome to this video of Senior Physics on Light and Waves. In this video we're going to explore the idea of path difference. Now path difference basically can be utilised to determine whether an object sitting on a specific position from a two-point source is going to be sitting on an antinode or a nodal point. Okay, so what we're going to do is use the idea of having monochromatic light here, and we're going to look at what is going to be produced on the screen. So we all know that if we take a two-point source, we're going to get a standing wave of antinodal point, which is going to sit right in the middle between the two point sources. So what we need to do is to measure the distance from point A, or source A, to point P, and then we have to measure the distance from point B to point P. So there's my two lines, A to P and B to P. So we measure this with a ruler, and then we know that that's going to produce a standing wave. That standing wave is going to be a constructive standing wave. Now if I take those two distances away, because they're equidistant to P, what we will find, that will give us the path difference. Now in this case, when we're looking at point P, which is directly in between the two point sources, we find that there is no difference in the path length. Point AP is the same length as point BP, so the path difference is 0. This means that the fringe pattern at that point P is given the order 0. Okay, so let's look at the next point. Now the next point, or the next fringe pattern, would be at Q1 or Q2. So what we can do here is exactly the same thing. We measure the distance from A to Q1 or A to Q2, and from B to Q1 or B to Q2, making sure that in each case we're going to the same point. And what we will find, if I do A to Q1 minus B to Q1, that will give me a path difference, but I can also do A to Q2 minus B to Q2, which will also give me the same path difference. One will be negative, the other will be positive. All that means it's either above the 0 order or below the 0 order. Both of those will produce a standing wave as they interact. Remember, they're coherent, so they will be in phase with each other, and hence they'll produce an antinode. But what we notice is that for this second fringe that is going to be produced, when we do the path difference is going to be equal to 1 wavelength. Okay? Remember, it's not equal to 1, it's equal to 1 wavelength. Now, you may be given the wavelength in a problem, and then you would, let's say the wavelength happened to be 2 meters. The difference between AQ1 minus BQ1 in this case would be 2 meters, which is that wavelength. So both of these fringe patterns are given the order 1. Now we can call one negative and one positive, just denoting whether it's above or below or to the left or the right of that order. Okay, so that deals with the next fringe. So what happens with the next fringe, or antinode 3? Well, in this case, I'm going to call that point R. So again, we do exactly the same thing. I measure the distances from A to R1 and B to R1, or I do the same for the other one at the bottom. This is going to produce a standing constructive wave. We can go to the bottom line, A to R1 or B to R1, and that will also cause a second fringe pattern. They are equidistant from each other. They produce 2 standing waves which are constructive, so we get 2 antinodes. Now, when I basically work out the difference between these two lengths, AR minus BR, doesn't matter which one we're talking about, the result is they're going to be 2 wavelengths different from the standing constructive wave that we had at point P. So as I said to you, if the wavelength happened to be 2 meters, in this case, the difference between AR1 and BR1 will be 4 meters. Divided by 2, that means we've got 2 wavelengths difference between them. So they're given the order, or these fringe patterns are given the order 2. As a result, this can continue throughout the range of different antinodes, going to 3 wavelengths and maybe even 4 wavelengths. So that basically explains what happens with respect to antinodes. What happens though with nodes? So in this case, we're going to do the same sort of thing. Now, what we're going to be doing is the node is going to sit between point P and Q1 and Q2. Okay, I'm going to call it S1 and S2. So that's where I'm going to find my antinode. So I measure again the distance from A to S1 and B to S1. Again, that will give me a standing, but in this case, destructive wave. And I've just outlined that in the yellow box because basically when we're dealing with light, that will be a black area. I'll also get exactly the same if I go from A to S2 or B to S2. This will produce again a standing destructive wave or a nodal point. Now when I actually work out the difference between these two paths, AS minus BS, doesn't really matter whether I'm talking about 1 or 2. As I said to you, it's either going to be positive or negative value. They'll be the same value. But what we'll notice is that the path difference in this case will be half a wavelength. So as I said, the wavelength happened to be 2 meters. The difference between AS1 minus BS1 or AS2 minus BS2 in this case would be 1 meter. That means that's half a wavelength. Now they're not really given orders, but basically all you need to understand for nodes is they're going to be half a wavelength difference. So let's look at the next nodal point beyond order 1 of the antinodes. Okay, so in this case I'm going to call this T1 and T2. So again, I measure the distance, A to T1 and B to T1, and that will give me my second antinode, second node, beg your pardon, or I can go from A to T2 and measure the distance B to T2 and take the 2 away. They will also give me a second nodal point. Now in this case, when I take the 2 lengths away, AT minus BT, the path difference in this case will not be half a wavelength, it will be 1.5 wavelengths. So as a result, we can call these nodal points 1.5 wavelength differences. So in this case, if the wavelength is going to be 2 meters, the result is the difference between AT1 and BT1 or AT2 and BT2 is going to be 3. Okay, noting that 2 will be for the one wavelength and then a half for the second bit, so hence it's 3 meters. And that continues all the way through. So the next antinode will be 2.5, the next node will be 2.5, the next node after that will be 3.5, and so forth and so on until eventually it gets round to the side where you're not going to get any waves interference. Okay, well I hope that makes sense. So in this case, what you'd then be able to state is if you know what the path difference is, you will know whether you are sitting on either a nodal point, because it's going to be a whole wavelength difference, or you'll know if you're sitting on an antinodal point, because that's going to be a whole wavelength difference, whether it be 0, 1, or 2, or 3, or you're going to be sitting on a nodal point, which is going to be half a wavelength difference, either a half, 1.5, 2.5, 3.5. And by combining those together, you'll be able to work out what is likely to happen. So what I suggest you do is you do need to learn these path differences, because then it gives you a better understanding as to what's going on. But remember, we're always talking about wavelengths, not 1 meter or 2 meters. It's 1 wavelength and 2 wavelengths, okay? So I've put this summary sheet there for you to work your way through, and basically just go away and learn. And remember, it's going to go from the center. 0 is going to be your antinode, then you've got your 1 wavelength differences, your 2 wavelengths, and then your 3 wavelengths. And for nodal order, it's going to start off at half wavelength, 1.5 wavelength, 2.5 wavelength, etc., etc. Now, it makes sense that why the nodal point is half a wavelength difference is because you've got to have a crest meeting a trough at the same time so they cancel out. So it's got to be half a wavelength out in order for that to occur. Okay, so what I suggest you also do is have a look at the exemplary video which I'm going to be posting up, and that will run through a few problems and show you how you can use path difference. Well, that basically concludes everything that we've worked on with respect to the light and waves unit. Hope you found it interesting. There is one more post on wave-particle duality, which is basically a lecture which I think you might find interesting. The key point is that at this stage we only know that light has travelled in the form of waves, but later on in the units you will find out that there is evidence to show that light also travels in the form of particles put forward by Einstein and Planck. And they put forward evidence to say that there are particles called photons, and there we've got two pieces of evidence, one showing light travelling in waves and one showing light travelling in the form of particles. Which one is which? We don't really know. It's more of we've got evidence for both. Okay, so there's a discussion on that. I hope you've enjoyed it. Thank you for signing up for the course, and please feel free to rate it and drop me an email if there's anything that you'd like extra which is involved in this course. So thanks for watching.